Hi, welcome to my video. In this video, I'm going to start with linear algebra. Linear algebra is very essential nowadays as it will be very helpful for machine languages and programming. So under linear algebra, the first chapter is going to be vector space. So before going for the definition of vector space and examples and then theorems followed by them, we'll start with internal composition and external composition of vectors. So internal composition means it's called vector addition. Internal composition refers vector addition. This operation takes two vectors from a vector space and then produces another vector within the same space. For examples, if I take two vectors u and v from a vector space, then u plus v, that is another vector I will be getting, that vectors also must be in the same space. Then it is called internal composition. For external composition, this operation takes a scalar, that is we are taking a constant. Scalar is nothing but a constant number from the field f and a vector from a vector space, and both of them we combine by multiplication, scalar multiplication, and produces another vector within the same space. That is, for example, if we have a vector v and a scalar c, then c star v, this also can write it as c dot v, also must be a vector within that space. Then it is going to be called as an external composition. The simple way of understanding is internal composition refers vector addition and external composition refers scalar multiplications. Now we'll go for the definition of a vector space over the field f. So let V be the set whose elements are called vectors and f be a field whose elements are called scalars. The set V is called a vector space or linear vector space over the field f if V of f satisfy the following conditions. So V of f in the sense is a vector over the field f. What we need to know is from the set V, whatever the element you choose from V must be vectors, and then the elements are from f are going to be called scalars. So, and when it is going to be the vector space means it must satisfy the following all these conditions. The first condition is V plus is an abelian group with respect to internal composition plus, and V of f is closed under its scalar multiplication with respect to dot, that is the external composition. For any a in f, alpha in v, a dot alpha, scalar multiplication is equal to alpha dot a, and let me take that as b, vector b, and that belongs to v. And the third one is v plus dot. Now we are combining two structures. V plus is addition and multiplication. So satisfying the following condition. Number one is for a alpha dot belongs to v. That means a comes from f and alpha comes from v, and if you multiply with them with a dot alpha belongs to v. The second one is going to be a into alpha plus beta is equal to a alpha plus a beta for all a in f, and alpha beta belongs to v. A are going to be scalars, alpha beta are going to be vectors. That means scalar multiplication is distributive over vector addition. And then third one is going to be a plus b into alpha. So that must be equal to a alpha plus b alpha. Alpha comes from v and a and b comes from f. A, b are going to be scalars, alpha is going to be the vector. So what is the meaning of this statement is multiplication by vector is distributive over scalar addition. So that is what a plus b into alpha is equal to a alpha plus b alpha. And then next one is going to be ab into alpha. So ab into alpha is equal to ab into alpha. That means multiplication is associative. A into b alpha is equal to ab into alpha. And then here last one is going to be 1 into alpha is equal to alpha. Here alpha belongs to v and 1 is the unit element of f. So unit element of f is a scalar, so obviously 1 will act as the unit element. Unit element means if you multiply with any other element, the same element will be back and it belongs to f. Then 1 will act as the unit element for f. The identity element under plus is denoted by 0 and it is called 0 vector or null vector, which is also unique. So in terms of plus, the identity element is going to be 0. In terms of dot multiplication, 1 is going to be the unit element. So this is what overall definition about vector space. So to summarize, first we need to know what is the internal composition and external composition, and then from then on we are going to define the definition for vector space. So for vector space, all these conditions should be satisfied. So the first one is going to be where is an abelian group under addition. Second one is going to be V f is closed under its scalar multiplication. Third one is V plus dot satisfy following condition: A into alpha belongs to V and A into alpha plus beta is equal to A alpha plus A beta. A plus B into alpha is equal to A alpha plus B alpha. And then the scalar associative property: A into B alpha is equal to AB into alpha. 1 into alpha is equal to alpha. So when a set satisfies all these conditions, then it is going to be called as a vector space over the field F. So examples are a little big. So in my following video, you can see all the examples how we can prove the given set V with respect to the field F is going to be a vector space. Thanks for watching this video. See you in the next video.